welcome. We're going to see the two category classification example, neyman criterion and minimax criterion. So there are consider two classes, two actions, alpha 1 and alpha 2. And the true classes are alpha 1 when it is w1 and alpha 2 when w2. R of alpha I given x is equal to risk is sigma j equal to 1 to c lambda alpha I given wj p of wj given x, risk formula. So R of alpha 1 given x, so we write for alpha 1 and alpha 2. Let lambda of alpha 1 given wj is lambda 1j and lambda of alpha 2 given wj is lambda 2j. So R of alpha 1 given x is sigma j equal to 1 to c lambda 1j p of wj given x, and that's expanded for 1 2. Lambda 1 1 j equal to 1 and j equal to 2, the equation is expanded. Same way we write for R of alpha 2 given x and it is expanded. Fundamental rule to decide W1 class is R of alpha 1 given x must be less than the R of alpha 2 given x. So this equation should be less than this equation. So bringing P of W1 given x as common, this becomes lambda 1 1 minus lambda 2 1 is less than, and the other side P of W2 given x is made common. So lambda 2 2 minus this lambda 1 2 comes to the right side. So now fundamental rule to decide W2 is the same thing opposite. So this side should be greater than the right hand side to decide the class W2. Minimax criterion. Sometimes you must design a classifier to perform well over a range of prior probabilities. Bayesian theorem states that we need the prior probability for knowing the class. So when we may not have the prior probability, the minimum criterion when the overall risk, the maximum overall risk will be R is equal to Cauchy integral R alpha of x given x p of x dx. So when p of x is 1, rewrite the equation, and then for two classes w1 and w2 and two actions corresponding alpha 1 and alpha 2, R is integral alpha 1 given x dx plus R of alpha 2 given x dx. So the same equation we had in the last one. R of alpha 1 given x is this one, lambda 1 1 p of w1 given x plus lambda 1 2 p of w2 given x, and R of alpha 2 given x. So R is equal to add both, and then p of w2 is 1 minus p of w1. So use that and rewrite the equation. This is for minimax criterion, the final equation is required. And then Neyman-Pearson criterion, we may wish to minimize the overall risk subject to a constraint. So minimize the total risk subject to the constraint R of alpha I given x dx. The risk for alpha I is less than some constant for some particular I. So we generally satisfy a Neyman-Pearson criterion by adjusting the decision boundary. NP classification is a binary classification that addresses the asymmetric errors in the classification problem. So let x, y be a random variable where embedded image x is a vector of feature and y belongs to class 0 or 1 represents the binary class label. So it's divided into training and data set. Phi of dot is the mapping embedded to the image which returns. So the final equation for Neyman's criterion is if R of phi equal to P of theta of x not equal to y, for y equal to 0 it's type 1 error and y equal to 1 belongs to type 2 error. So embedded image with upper bound on type 1 error is alpha, then R naught of theta is less than alpha into R1 of theta and the opposite. Thank you.